Introduction to Private NAT. Please consider subscribing to the channel. I produce videos daily covering AWS, Azure and GCP. Also hit the notification bell to get notified of new videos. I appreciate in advance your subscription. Welcome to our deep dive into GCP Private NAT. Today we're going to solve one of the most challenging networking problems in cloud environments. Imagine you're a cloud architect and your company just acquired another business. Both companies have been running their infrastructure on GCP with the same IP address ranges. Let's say both are using 10.1.1.0/24. Now you need to connect these networks so they can communicate. But GCP's VPC's peering has a fundamental rule: no overlapping IP ranges allowed. This is where Private NAT becomes your superhero solution. Think of Private NAT as a translator sitting at the border between your networks, changing the from address on packages so they can be delivered to the right destination without confusion. The overlapping IP problem. Let me paint you a picture of why this problem exists. When you have two VPCs with the same subnet ranges, it creates what we call routing ambiguity. Picture a virtual machine in VPC trying to send traffic to IP address 10.1.1.6. The router looks at its routing table and thinks, wait, 10.1.1.6 could be in my local subnet, or it could be in the peered VPCB. This confusion makes routing impossible. It's like having two John Smiths living at 123 Main Street in different cities. The Postal Service wouldn't know which one to deliver to without additional context. This is why GCP simply refuses to create VPC peering connections when IP ranges overlap. The diagram shows exactly what happens. The peering connection fails before it even starts. Private NAT Architecture Overview. Now let's look at how Private NAT elegantly solves this problem. The key insight is that we need to translate the source IP address before it crosses the peering boundary. Here's how it works. When Virtual Machine sends a packet to 10.1.1.6, the Private NAT gateway intercepts it and performs source NAT, SNAT. It replaces the original source IP with an IP from a clean, non-overlapping range. Think of it like a diplomatic translator. When Virtual Machine A says hi, this is 10.1.1.5 calling 10.1.1.6. The NAT gateway translates it to hi. This is 192.168.10.5 calling 10.1.1.6 before sending it to VPCB. VPCB receives the packet, processes it, and sends the reply back to 192.168.10.5. The NAT gateway then translates it back and delivers it to the original Virtual Machine A. This creates a clean communication channel without any IP conflicts. Key components deep dive. Let's break down the essential components that make Private NAT work. Understanding each piece is crucial for successful implementation. First, we have the cloud router. This is like the foundation of your NAT setup. Every cloud NAT gateway must be attached to a cloud router, which handles the routing logic and advertises routes. The cloud NAT gateway is configured with type equals private, which tells GCP this isn't for internet access but for private-to-private translation. The NAT rule is where the magic happens. It's the brain that decides when traffic from subnet X is going to destination Y. Apply NAT using range Z. Your source subnet contains the virtual machines that need to communicate across the peering connection. The NAT subnet is crucial. It must be completely non-overlapping with anything in the destination VPC. Think of it as your clean address space for translation. Detailed traffic flow. Let me walk you through exactly what happens to a packet as it travels through our Private NAT setup. Step 1. Virtual Machine A at 10.1.1.5 wants to reach Virtual Machine B at 10.1.1.6. It creates a packet with source 10.1.1.5, destination 10.1.1.6. Step 2. The packet hits our Private NAT gateway. The gateway checks its rules and finds a match. Destination is 10.1.1.0/24. so I need to apply NAT. Step 3. SNAT is applied. The gateway picks an available IP from the NAT subnet 192.168.10.0/24. Let's say 192.168.10.1100, and rewrites the packet header. Now it shows source 192.168.10.1100, destination 10.1.1.6. Step 4. The modified packet travels through the VPC peering connection to VPC B. Step 5. Virtual machine B receives the packet and sees it came from 192.168.10.1100. It processes the request and sends a reply back to 192.168.10.1100. Step 6. The reply packet travels back through the peering connection and hits our NAT gateway again. Step 7. The gateway performs reverse NAT, changing the destination from 192.168.10.1100 back to 10.1.1.5, and delivers it to virtual machine A. Creating VPCs with overlapping subnets. Let's start implementing our private NAT solution step by step. First, we need to create our problematic scenario: 2 VPCs with overlapping IP ranges. We'll create VPC-A and VPC-B, both using the 10.1.1.0/24 range. Notice that we're using subnet mode custom because we need precise control over our IP ranges. The range parameter defines our subnet CIDR. This is where the overlap occurs. Both subnets use exactly the same range. At this point, if we tried to create VPC peering between these networks, GCP would reject it with an error about overlapping IP ranges. We're also specifying region US Central 1 for both subnets to ensure they're in the same region where we'll set up our NAT gateway later. Creating the NAT subnet. Now comes a critical step: creating our NAT subnet. This subnet is the secret sauce that makes private NAT work. Notice the purpose equals private NAT flag. This tells GCP that this subnet is specifically designed for NAT operations, not for regular virtual machine deployment. The IP range 192.168.10.0/24 is carefully chosen. It must not overlap with anything in VPC-B, our destination network. This is your clean address space. Think of this subnet as a pool of translator addresses. When the NAT gateway needs to mask the identity of a source virtual machine, it picks an available IP from this pool. The size of this subnet determines how many concurrent connections you can handle. Each active connection consumes one IP from this pool. Setting up cloud router. Before we can create our NAT gateway, we need a cloud router. Think of the cloud router as the control plane for our NAT operations. The router needs to be in the same region as our subnets. That's why we specify region equals US Central 1. The network parameter associates this router with VPC-A, which is where our source virtual machines live and where we need NAT functionality. Cloud routers in GCP are more than just NAT hosts. They can handle BGP routing, VPN connections, and interconnects. But for our private NAT use case, it serves as the anchor point for our NAT gateway. You can think of it as the brain that will make routing decisions and host our NAT functionality. Creating the private NAT gateway. Now we create the heart of our solution, the private NAT gateway. This command has several important parameters we need to understand. The type private flag is what makes this a private NAT instead of a regular internet NAT. This tells GCP we're doing private to private translation. NAT IP allocate option manual only means we're explicitly controlling which IP ranges to use for NAT, rather than letting GCP auto-assign them. NAT custom subnet IP ranges. Subnet A for NAT tells the gateway to use our specially created NAT subnet as the source of translation IPs. This gateway will now sit in the data path, ready to intercept and translate packets based on the rules we'll create next. Think of this as deploying your translator at the border checkpoint between two countries. Creating NAT rules. The NAT rule is where we define the translation logic. This is probably the most important configuration in our entire setup. The match parameter uses a CEL, Common Expression Language, expression to define when NAT should be applied. In our case, destination IP equals 10.1.1.0/24 means apply NAT when traffic is destined for the overlapping subnet in VPCB. Source NAT active ranges equals subnet. A overlapping specifies which source subnet's traffic should be subject to this NAT rule. So this rule reads: when traffic from subnet A overlapping is going to 10.1.1.0/24, perform NAT using IPs from our NAT subnet. You can create multiple rules for different destination ranges or different source subnets. This gives you fine-grained control over which traffic gets translated and which doesn't. The rule acts like a smart filter that only translates traffic that would otherwise cause routing conflicts. Creating VPC peering. Now comes the moment of truth. With our private NAT fully configured, we can finally create the VPC peering connection that would have been impossible before. Notice that we create peering in both directions. This is standard for VPC peering. The peering A to B allows VPC A to reach VPC B, and peering B to A allows the reverse. Here is the magic. Even though both VPCs have overlapping 10.1.1.0/24 subnets, the peering succeeds because VPCB never sees traffic from the overlapping range. Thanks to our NAT gateway, all traffic from VPCA appears to come from the clean 192.168.10.0/24 range. From GCP's perspective, there are no routing conflicts because the effective source range, 192.168.10.0/24, does not overlap with anything in VPCB. This is like having diplomatic immunity. The NAT gateway gives our traffic a new identity that is acceptable in the destination network. Testing connectivity. Let's create some virtual machines and test our private NAT implementation. This is where we prove that our solution actually works. We'll create virtual machine instances in both subnets with overlapping IP ranges. Notice that we're placing them in specific subnets using the subnet parameter. The key test will be connectivity from virtual machine A to virtual machine B without private NAT. This would be impossible due to the overlapping ranges. We also need to create firewall rules to allow our test traffic. The rule allows SSH and ICMP from any source in the 192.168.10.0/24 range. This is the translated source range that VPCB will see. Remember, virtual machine B will never see traffic from 10.1.1.0/24 directly. It only sees the translated addresses from our NAT subnet. When we test with ping and SSH, we'll see the private NAT working transparently in the background. Bidirectional setup. Our current setup only allows VPCA to initiate connections to VPCB, but what if virtual machines in VPCB need to initiate connections back to VPCA? This requires a symmetric private NAT setup in VPCB. We need to create the same components: a NAT subnet, cloud router, NAT gateway, and rules. The key difference is the NAT rule. In VPCB, we match traffic destined for 10.1.1.0/24, VPCA's overlapping range, and translate it using a different non-overlapping range, say 192.168.20.0/24. This creates a bidirectional translation system where both VPCs can initiate connections, but neither sees the other's overlapping ranges directly. Think of it like having translators on both sides of a border. Each side speaks in their local language, but the translators ensure clean communication across the boundary. This is essential for applications that require bidirectional communication. Advanced NAT rules. Private NAT rules are incredibly flexible. You can create sophisticated matching logic using CEL expressions to handle complex networking scenarios. For example, You might have multiple overlapping subnets in the destination VPC. You can create separate rules for each one, using different NAT IP ranges for different destinations. The CEL expressions support logical operators like and or, allowing you to create rules like apply NAT if destination is in range A or range B. You can also match on source criteria beyond just the subnet. For instance, you could apply different NAT rules based on the source virtual machine's network tags or other attributes. Port-based rules are also possible. Maybe you want to NAT HTTP traffic differently than database traffic. This flexibility makes private NAT suitable for complex enterprise scenarios where you need fine-grained control over network translation policies. Monitoring and troubleshooting. When something goes wrong with private NAT, you need the right tools to diagnose the issue. GCP provides comprehensive monitoring and logging capabilities. Cloud NAT logs show you exactly which packets are being translated, including source and destination IPs before and after translation. This is invaluable for troubleshooting connectivity issues. VPC flow logs complement NAT logs by showing you the complete packet journey through your network. You can see if packets are reaching the NAT gateway and whether they're being translated correctly. Cloud monitoring provides metrics on NAT gateway performance, including connection counts, packet rates, and error conditions. Common troubleshooting scenarios include packets not being translated. Check your NAT rules. Connections timing out. Check firewall rules in destination VPC. And performance issues. Check NAT subnet sizing. The logs will show you exactly what's happening to your packets, making debugging much more straightforward than guessing. Limitations and considerations. Private NAT is powerful, but it has important limitations you need to understand before implementing it in production. The biggest limitation is protocol support. Private NAT only works with TCP and UDP/ICMP, for example ping, and other protocols are not supported and will be dropped silently. Application awareness is another key consideration. Applications in the destination VPC will see connections coming from the NAT IP range, not the original source IPs. This can break applications that rely on source IP for authentication, logging, or load balancing. Private NAT is unidirectional by default. If you need bidirectional communication, you must set up NAT in both VPCs, which doubles the complexity and cost. Performance can be impacted since all traffic goes through the NAT gateway. This creates a potential bottleneck and single point of failure. Cost is also a factor. You pay for the cloud NAT gateway, plus data processing charges for every packet that gets translated. Cost analysis. Understanding the cost implications of private NAT is crucial for budget planning and architecture decisions. The base cost includes the cloud NAT gateway fee, which is charged per hour regardless of usage. This is typically around $45 per month per gateway. Data processing fees are charged per gigabyte of data that flows through the NAT gateway. This can add up quickly in high-throughput environments. Expect around $0.045 per gigabyte processed. If you implement bidirectional NAT, you're paying for 2 gateways plus processing fees in both directions. Consider the NAT subnet size carefully. Larger subnets support more concurrent connections but don't directly increase costs. However, running out of NAT IPs will cause connection failures. Compare this to the alternative costs: renumbering existing networks, maintaining separate environments, or using expensive dedicated interconnect solutions. For many M&A scenarios, private NAT provides significant cost savings compared to network renumbering projects. Real-world use cases. Let me share some real-world scenarios where private NAT has been a game-changer for organizations. In merger and acquisition scenarios, Company A acquires Company B, and both have established GCP environments using common IP ranges like RFC 1918. Rather than spending months renumbering one of the networks, private NAT enables immediate connectivity while long-term integration planning continues. SaaS providers often face this challenge when offering VPC peering to customers. They can't control customer IP addressing, so private NAT allows them to handle overlaps gracefully. Multi-cloud scenarios are another common use case. When connecting GCP to other cloud providers or on-premises networks that use conflicting address spaces, private NAT provides a bridge. Development and staging environments often mirror production IP ranges. Private NAT enables these environments to communicate for testing purposes without requiring separate address spaces. The key pattern is: whenever you need network connectivity but can't control or change the IP addressing on one or both sides, private NAT provides a solution. Best practices. Based on real-world implementations, here are some key best practices for private NAT deployments. Plan your NAT subnet carefully. Choose ranges that definitely won't conflict with future network expansions. Document these ranges clearly, since they become part of your network architecture. Size your NAT subnet based on expected concurrent connections, not total virtual machines. Each active connection consumes one NAT IP, so plan for peak usage scenarios. Implement comprehensive monitoring from day one. Set up alerts for NAT gateway utilization, connection failures, and unusual traffic patterns. Consider security implications carefully. Applications in the destination VPC see traffic from NAT IPs, so ensure your security policies account for this. Document your NAT rules thoroughly. Complex cell expressions can be hard to understand months later, so include clear comments about what each rule does and why. Test failover scenarios. What happens if your NAT gateway fails? Consider deploying multiple gateways for high availability. Plan for the future. Private NAT should be a bridge solution while you work toward long-term network standardization. Summary and troubleshooting guide. We've covered a comprehensive implementation of private NAT to solve overlapping IP address challenges in VPC peering. Remember the key components: cloud router, private NAT gateway with type equals private, NAT rules with CEL expressions, and a properly sized NAT subnet with purpose equals private NAT. Common issues include NAT rules not matching traffic. Check your CEL expressions. Firewall rules blocking translated traffic. Remember destination VPC sees NAT IPs. And connection exhaustion. Check NAT subnet sizing. Quick troubleshooting steps. Check NAT logs to see if translation is happening. Verify firewall rules allow traffic from NAT IP ranges. Confirm VPC peering is active. And monitor NAT gateway metrics for errors. Private NAT is powerful but complex. Use it when you truly need it, when IP renumbering isn't feasible. For new deployments, proper IP planning is always preferable to NAT translation. The key takeaway: private NAT transforms an impossible networking scenario into a working solution, enabling business continuity in challenging situations like mergers, acquisitions, and third-party integrations. If you have not subscribed to the channel, please do. I produce videos daily on AWS, Azure, and GCP also. Hit the notification bell so you get notified of new videos. Thank you for your attendance. I appreciate in advance your subscription.